Hello, I'm Taryn from Driver Assist Tech, the organiser and marketing partner for today's session. Thank you for joining us for this Motion Data hosted webinar on this exciting topic, revolutionising front crash prevention testing with the MDTR-TR. The information presented in this webinar will be available after the session, but if you would like further details, please get in touch with us. Now over to Ed.
Hi everybody, just a few house rules before we go through with things. Welcome, thank you very much for joining us today. As Taryn said, the webinar is being recorded. If you have any questions or would like to chat, please use the chat feature and please put questions in Q&A. We will be going through those at the end, and after we've gone through a few of those questions, we'll be able to have discussion time at the end of the meeting. So that's just, and you'll all be muted until that point. So, and now we can progress to the actual presentation. So, Steve and Paul.
Good morning.
Morning.
Hi, we're here today to talk about our MDTR-TR, which is the truck trailer target. It was originally designed for the front crash prevention test, which is performed by IIHS, which was originally meant to be a test of the forward collision warning because they were using a real truck. So once the activation of forward collision warning, it was deemed as a success, and the vehicle then drive around the real trailer. Of course, we all know that driving against a real trailer is not a good idea, because with all the best drivers in the world, there's still a possible instance might happen where the collision with the object might occur. So we looked into designing a suitable surrogate target to replace the real trailer. So we talked with IIHS. We asked them what their requirements would be. One of the requirements was it had to be almost a full scale. I tried to get them to be 80%, but no, they wanted it at a full scale. So, as you know, a full scale of a trailer target is around 4 meters high, about 2.4, 2.5 meters wide. So this presents problems. Of course, the design process, we had to think about how do we make something that big? How do we make it stable? How do we have a good radar signature? How do we make it that we can be usable? We could make it similar to the Soft Car 360, where it has exploded into lots of pieces. But then you have the problem, how do we put the last piece on the top where it's 4 meters high? How do we build it on a test track if you've hit it, without having cranes and forklifts and various things? So we started to look at a simple slab like the EBT, making a bigger slab, but that didn't have issues with stability, and then you think, well, I have to make it wider and taller, but also it didn't have the overhang and the protection for the right signature for the radar. So we had to work on it. So we thought the concept would be, let's have an inflatable part of it and foam part of it to create the signature, because the bulk of a trailer is empty. It's an empty trailer, so the top half of it is just purely there for vision and size. So we decided, well, let's not use that to our advantage. That most of the radar signature is down low by the wheels and down by the bed and down by the axles, and the actual load area of the trailer is just an empty shell. So why not have that empty shell inflatable? Because that gives us the shape without all the issues of trying to put the last bit on top. So we came up with this concept of part foam, part inflatable. And so, as we can see in this current slide, that the rear view has to be the height the same, and so that part of it at the back was very high in shape of the original trailer. So we thought, well, we can make that, as I said, inflatable, and therefore it also packs up smaller and it's easier to transport and move around the test track. So we came up with this concept there that we'll have a bare inflatable shell, and then we'll be able to add an image to that, because the inflatables have ribs in them where they stop them inflating. And then we can add the images to that to make it more realistic, the wheels, the tailgates, the sides. And this aspect also allows us to tailor that. So we have the custom colours. The IIHS colour is a white Vanguard trailer. There's no reason why it can't have a red rear end. We can have a white side, red side. You can, because the side's not that important in the object of it, you can have it branded with your own company logo, wherever you want. We can also then look at making the image on the back have writing on, changing the image. You can have it the local image. We've seen truck trailers driving around with pictures of rhinoceroses on the back. You can have that on there as well. So we then want to know how we're going to hold it down. So we decided that we're going to add some weight to this structure. And so we can put that a base underneath it. So that was basically going to be that. Then how do we connect it to that base? So it's connected to the base with a foam inserts, which have poles up inside it, pretty similar to our SFD and our wall targets. So now that the nylon base is attached to that inflatable is attached to the base. So therefore, if you hit it, it's all going to slide along. And of course, the other aspect of it is how do we inflate it? Well, it's inflated with what we call a cold air system, which is a bit like a child's bouncy castle that constantly feeds air into the system, and it needs a blower. So we were worried about that blower being an object to an issue for the car's detection. So we have it at options of left-hand side and right-hand side. It's low and it's grey, so it blends into the tarmac, so the cameras don't see it so well. It's round, so it doesn't have a good radar signature, and it's at an angle of about 35 to 40 degrees coming off there, so any radar signature bounces off it. So you can have that object away, and it's about 20 meters long, so it's well away from the target itself. And also the tube is attached by a Velcro, so if you just get impacted, it disconnects and it doesn't drag the blower or the power system down the test track. So we've used those characteristics to reduce that visibility of the tube and the object as well. And we even had a design to put a cover over the blower that you can pretend it's a litter bin on the side of the road or a power unit on the side of the road. So after all these design work, we came up with the final design, which is the one you can see here. So this is the TRTR, the first prototype that we took to IIHS for testing. And you can see it has all the replication, characteristics of a dry Vanguard trailer. It's the right overhang, has the bumper element underneath for the under-eye protection. It has the right imagery, it has the right dimensions, and as Paul will tell you in a minute, it'll have the right radar signature as well. And obviously the LiDAR aspects are there as well for the right and infrared reflectivity. So as members of the World ISO committee, we took the, we call it the ISO methodology of making a target and applied that to this. So it has the right characteristics in all the sensor needs, and it will also be the correct dimensions for camera, for aspects for the LiDAR, the IR, and the radar signature. So if there was to be an ISO standard, it would conform to that. So I'm going to pass you over to Paul now, who's going to talk a little bit more about the actual radar aspects of it. So I'll move on to that next slide and pass on to Paul.
Hello. Okay, so basically, as Steve said, we can now deconstruct what we've built into a concept, and that's where we started. We basically thought to ourselves, what do we need to create? So the idea is a 3D depth perception. So from the rear end, the radar and other sensors will need to see this as though it's a real dry van trailer, which means it needs the depth element. So some work we previously did was around types of materials and high-tech metallic and conductive materials. And using those, we've been able to tailor various aspects of the signal strength into various parts of the target to give the depth element. So you can see here, there are very small green sections of high-tech material, and these build up the layers in the bed to give the bed of the actual trailer the strength of signal that it needs. And with the main supporting walls, as you can see here, are not facing to the rear. They're facing sideways so that the signal appears to be empty. So that what you've got is in effect an empty trailer. Moving on to the next one here, you can see how it's deconstructed at the bed and the 4 feet and the rear side. Now the rear side of this is similar in construction to our existing targets, as their properties are very much the same vehicle to vehicle with the metallic doors. So we use the same stuff that's tried and tested for the IR and RCS signature on the rear. For the wheels, we've actually got metallic material facing rearward to add strength to the axle location. And during the design phase, we added more to that because we believed we needed to enhance it even further. So you can see those there with the foam blocks. Looking at this, you can see the dimensional element, and this is what we're trying to replicate and for the radar to see. And you can see on here that the radar can actually see underneath between the 2 wheels, which again is another realistic aspect of what a real trailer. So it needs to be able to see underneath as well as it needs to be able to see the rear wheels, the axle, and the rear end of the target. And here is the actual radar data that we've done. We've got more tests to do, which we'll be doing later this year. We can tailor this to particular types of trailers if need be, but this is a product that IIHS needed, and it's tailored to that. And you can see here that the signal strengths are at the rear end, at the rear axle, exactly as we were aiming to do. And then there's another one that reads towards the end of the trailer. So these are the strengths that we're seeing on the radar. These are all taken at the fixed range 180 degree at 30 meters using a Continental ARS 408. You can see the crucial element is that it is reporting the depth at 2.8 meters between the rear end and the axle, which was what we were trying to achieve. So that's how that worked. And this is an example of a real trailer that we did some tests on. And here it shows the 2.5 meter depth element here. And you can see that that's how it represents a very similar construction to the radar. And that actually proves to be true when it's taken to the track. And then I'll pass you back to Steve for the actual work on the that we did at IIHS.
So we went to IIHS with the TRTR and successfully installed it. At the time, we had access to a Mazda, a Kia, and an Audi A4, which they were utilising for part of their testing, part of their front crash prevention tests. And we replicated the tests they'd already done with the real TRTR. One of the issues they found in the TRTR is they didn't like the very fact they had the overhang and they were driving really at it. So they actually modified the TRTR. I don't know whether they not modified the TRTR, modified the dry vanguard trailer. I'm not sure where people are aware that the rear axle, it can be moved along the bed, so it can be moved back towards that to reduce the overhang. And they actually did some tests with it. The early cars were with an overhang, and then they reduced the overhang because for safety aspects, they brought the wheels right to the back. So if there was a crash, the test vehicle wouldn't go underneath the trailer. So we had two sets of data to look at. The one they did originally with the overhang, and then also without the overhang. They drove the cars at the target. They used the inertial navigation system from Oxford Technical Solutions and some video software. They had some timing set up that once they got to a certain distance, if forward collision warning hadn't activated at that point, it was deemed as a fail. If it had acted at that point, it was deemed a pass, and they would drive around, swerve around the trailer. So we repeated that with all the vehicles, driving at from 10 kilometers per hour up to 70 kilometers per hour. And they drove at each trailer with each car and recorded the time. And then when we looked at the results later, we found that they all pretty much replicated the time of collision to the. There's a slight difference with the Audi, but we put that down to we were slightly early with the Audi because of the at the time we didn't have some lights. We added extra lighting for reflectivity. The Audi used lidars a lot. So in all the tests they did for the three cars, they all recorded pretty much exactly the same timing for the TRTR as they did for the Drive Vanguard trailer and then forward collision activation. Then we decided that one of the cars was actually working quite well and that was attempting to brake. So one of the drivers decided that we could do a full an A/B stop. So at 10 miles per hour, we did a 10 kilometers per hour, a A/B stop. It worked, and then we then carried on to do a full suite of 10 up to 70 kph again. I think we went up to 80 kph on that, driving at the car with the car at the trailer and stopped every turn. So that was something that I've never been able to achieve before, was driving at the trailer and let the cars stop because they had a fake trailer. They then did it with a couple of the other cars and also performed the same, did an A/B stop. So we were pretty happy and pretty confident that the vehicles were seeing our TRTR exactly the same as they were seeing the real trailer. The side-by-side test, we tested against the real trailer, it had all of those results. We double-checked them against the inflatable TRTR, and that was the same results came then. So, in effect, there was no difference between the two drivers for those three vehicles. So therefore, we're very confident that we have made a target that replicates a real truck trailer target. We have a video here. I'm not sure how I can play it. It will show that test. That's a little bit early. So if I'm going to share my screen, it might all go wrong for a few seconds here. But we didn't rehearse this. I'm just a bit of ad hoc in here. So
yeah,
I'm going to share my screen and play this video. So can you all see this video now?
Yeah.
Yep. So this is one of the vehicles that we used as a test at the time. 70 kph. So you can be 70 kph driving at the target. And the forward collision warning will activate. In the bottom of the screen, we have this green and red yes or no. So you've got the forward collision warning. Well, this is actually, sorry, this shows stop. This will show you stop, indicating stopped. That was the A/B stop against the vehicle target there. And now we're going to try and go back to the other screen. I'll stop the sharing. We back to the presentation now? No. So we're just going to load back up the presentation, and Paul's loading that back up. So I think we've got one or two more slides. And then we're going to open to some questions. So if anybody's any questions about the truck trailer target or the test, we can see there. Oh, sorry, we missed that bit there. Just jump forward one video. We're just going to go back one. This here is the actual being hit. That was the whole thing we did. How did we play that bit there, Paul? We decided that we'd use the Audi, so we blanked off the cameras of the Audi. Because it didn't have a radar and a LiDAR system, so we usually put some tape on the Audi sensors and then proceeded to then. So this is no insult to the Audi. It was fixed so we couldn't hit it. So we can play that little video of the crash again.
Yeah, I'm running it now.
Yeah, I'm not seeing.
You see it?
I'm not synced to presenter. No, but it's happening. Yeah, so as you can see, when it goes underneath there, it lifts the target up and then it hits the target. We've increased some foam elements at the bottom point now where it impacts at the bottom of the wheels and where the car hits it. It pushes the whole target forward, then it slides forward, detaches from the inflating tube and then just slowly deflates. And then you can just drag it back on the nylon base, which has got no friction, hit it with the inflated tube, and it just comes back up to full size. And so there's no real hard points at all to hit the car. It's not designed to be impacted in the same way a soft car 360 or an EBT or one of our other AB targets is, where it's going to hit and hit and hit and hit. It was designed originally for the IIHS, which is front crash prevention, and they were looking at forward collision warning. But it is soft that if anything goes wrong, you're not going to damage any cars or anything. But it's more designed for cars to have a serious amount of development already done, and they're not going to be deliberately crashing. And I think this is going to be a bit more in the future, where the bigger targets are going to be harder to be able to hit at the higher speeds because it's hard to make a big object and have less mass and be usable again and do no damage. So it is one of those situations where you can hit it. It's designed to be. It's designed to be hit. It won't damage the car. It will move out of the way. It will reduce the mass, but it's not something you want to be doing at 60, 70, 80 kph. Because the chances are you might not have a target left at the end of it or have some damage to the target. But if you're doing those type of speeds, the forward collision warning comes in well far enough in advance to swerve around, proven by the test by IIHS that at all speeds, FCW gives you the time to avoid the object. So moving forward, I think we have to start looking at how we test that rather than just crashing into them for fun. So now we'll move on to the questions. Have we got any questions, Ed?
So at the moment, nobody's actually got any questions under Q&A. So if anybody wants to raise their hand, we can unmute you and then you can ask questions. So we can do it that way as well.
Just open the mics up to everybody and have a chat.
Well, yeah, we can do it that way. Just if anybody has any questions, they can ask.
Just unmute everyone then.
Yeah, unmute all. It's not an unmute all.
I can't find an unmute also. I'm going from the bottom of
Yeah,
it.
same. I'm doing the same.
None of them unmuted on my screen. My screen only out. So has anybody got any questions they would like to ask? Shazawa, you don't have a question. I must have covered it all. That's a Jazam, listening. What are you, Daniel?
Martin, did you have something? I saw your video go on briefly.
No, we have no question. It was a great presentation, but we have this pre-presentation of you, so no, nothing.
Good.
Okay,
It was
good.
a bit quick. Quicker than we practiced. Because we're talking faster.
Customizable.
Hmm?
Customization.
Yeah, so just to talk a few more points about the target. One of the points there, you can see in this image we're looking at, it's got motion data printed on the side now. And that's on the actual skin of the target. It's when you see the ripples, the reason why there's ripples is because you have to sew the structure that Paul showed, those green internal walls, to prevent the structure from bulging. And the more walls you have, the more ripples you have, but smaller ripples, and then the tighter you can get. But obviously, it's a you're going to look at the aspect of cost and what we're going to charge of this. So the more sewing and the more there's a complex amount of sewing and development into this. The more walls you have, the more sewing you have, the more cost you have. And this is the same the reason why it's not what we call an airtight target. An airtight target is where you pump it up, seal the valve, and leave it. To make those seams something this big and airtight is a lot of money and a lot of complexity. To hot weld and seam all the seams, there's no air coming out of it. And then you have the issue, if you do have it airtight, if you get a hole in it, it's not airtight anymore. Where with the cold air, as long as you have more air going in than you do coming out, it will go up. So you can have rips and you can just put a piece of tape on it, or you have damage, you can just quickly sew it up or cable tie it together and put some tape over the top of it and reduce the amount of air coming out of it. So as long as there's more air going in than there is coming out, it will inflate. So if we go back to that image of with the motion data, the last page, where we're in control of the slide at the moment. So we've got the motion data printed on there. That is the skin of the actual target. The image on the back is Velcroed on. The wheels on the side are now Velcroed on. And we can also have a side there over the top of the motion data Velcroed on. So it has the same side print image as a real Vanguard trailer. It now does have all the print on there. It is printed. It's printed with motion data. It's printed with the rivets, the slats, all of you get on a dry Vanguard trailer. But you can actually put a side onto it. The Velcro's on there as well, which will give it an even smoother look and more realistic trailer side. But obviously the test is from the rear. The rear already has that slab. But that allows you to customize that target. So instead of having motion data there, you could have IIHS, Ford, Hyundai, whichever you want written on there, your test track, your UTAC test track, your ADAC test track. You have those sides printed there. Because as well as being a truck trailer target, it's also a very big advertising billboard. So when it sits on the track, it is 4 meters high, 6 meters long. And so it is a big object that people can see from all way. And you might well utilize that side image. And you could look at the back, you can change that back from the white rear IIHS image to a red truck, for instance. In the CNCAP world in China, they're looking at having a red rear truck target. And so we have that same image there. You can have the writing on the local haulage company that you work. You could have different characteristics, an image printed on the back, whatever.
Risken att ställa sig frågan att man trasslar in sig.
Steve, I have a question.
Yes.
This target, is it just from the back or is it from the side as well?
It was designed originally from the side, but it does have the same characteristics from the side as it should do. But the original test is all about the rear end collision, because the figures show that cars were driving into stationary trailers.
Okay.
The whole test was.
So, but you can use it as a, if you see it from the side as well.
You could, but as you see, it doesn't have the same silhouette as a trailer because of the slope at the front. And we added that slope at the front to reduce the wind load on it, reduce the mass, and reduce the volume, and also partially the cost from the extra material, extra sewing on that. Because there is a view that we can mount this on our flex towing system and tow it along, and therefore that would be moving, so that would reduce the frontal wind load by having that slope at the front. So it doesn't have the same visual characteristics as a truck on the sideways on because of that front.
Okay.
But I said the initial design and the initial tests in the world at the moment for AB on trailers and truck trailers is from the rear. Pretty much like we started with the CCRS for the EBT in 2013. This is like the next phase of that CCRS, except it's not car-to-car rear stationary, it's car-to-truck rear stationary. Because the stationary object from the rear is one of the hardest things to detect, because these things look like a road sign, and you talk to ignore a road sign, and then you stop one in the middle of the road, it's 4 meters high, looking like a road sign. The only thing it doesn't have written on it is Gothenburg 60 kilometers this way. So that's why the hardest test is the stationary object test, which is designed for. But so it can be customized into different, and we have different versions of it as well in the pipeline. So we have a shorter overhang. We can make it square. Once we have this concept, we can make a full size. And we've also looked at having a full size trailer with also a cab on the front, a truck. And we could therefore make it completely realistic to the side image of a trailer and a truck. And part of the reason we did for the bed object, when Paul analysed it, a lot of the radar signature was at the bottom end, the wheels, the beds, and all this stuff. So we looked at, well, if that's where it could be, a flatbed trailer would be easy to look at as well, because we just not put the big inflatable part on the top, still use the same characteristics of the bed, the wheels, the pedestals, and the mounting system. And then we could put any object on top of that bed. You put a JCB, a boat, or any other object you want to. So it's not just the final version, it's just the start version of various different objects we can look at as AAB develops in the future.
Okay, are there any more questions?
Well, I'm a very, very good presenter, or slides make perfect sense. And Paul's explanation was perfect.
Okay.
Would like to thank you for coming along and seeing our presentation. If anybody thinks of any questions afterwards and thinks, oh, I've got a question now, when you get off this, feel free to obviously get in touch, ask us. We can send a copy of the presentation. It's available. And thank you. Thank you for your time.
Thank you very much.